Last time we left off with this idea of principal ideal domain, PID, and PID is a place where every ideal is principal, meaning that it has a single generator. And then we had a couple of examples, right? And one of the examples I want to focus on or remind you, so Z bracket X is not a PID. That's probably the thing that we left off with last time, the last thing that I wrote down. And the reason is that we showed that the ideal generated by 2 and x is not principal. It cannot. There's not a single polynomial out there that can generate all the polynomials living in that ideal. Now, okay, so Z bracket X is not a PID, and I'm going to jump right to the following theorem. So this is 2710, and it goes like this: if F is a field, then F bracket X is a principal ideal domain, right? So let's contrast this statement right here with this one right up here, right? Z is not a field, Z bracket X turns out to not be a PID. But anytime, if your ring of coefficients for your polynomials is a field, right, then you're guaranteeing you got a PID. So for the proof, and this proof is kind of fun. So what do I want to say here? So yeah, let's let capital I be an ideal of F bracket X. All right, so what do I need to do? I need to find a generator for that ideal. Now let's get rid of the easy case first. If I happens to be the trivial ideal, then of course it's generated by the zero polynomial. So if I consists of just the zero polynomial, then of course I is equal to the ideal generated by 0. And so otherwise, I is going to have some non-zero polynomial in there. And so here's what I want to do. So what I want to choose, so I'm going to choose, let's call it g of x. I want to choose a non-zero polynomial g of x in I, and I want to choose it of least degree, right? So running around all throughout I, choose any non-zero polynomial that has least degree amongst all non-zero polynomials. So choose g of least degree. And so now what do we know? Okay, so we've got this polynomial g of x in there. One thing we know, so the ideal generated by g of x, and I can just put this in quotes, in fact. So the ideal generated by g of x is, of course, contained in I. And what we want to do is show that these are actually equal. So it turns out that by choosing any non-zero polynomial of least degree in the ideal, it will turn out to be a generator for the ideal. All right, so I need to get equality, which means that I need to show that I is actually a subset of the ideal generated by G. Okay, so that means that anytime I choose a polynomial over here, I need to show that it lives over here. So yeah, let's take some polynomial, let's say f of x in I. What do I need to do? I need to show that f of x is actually a multiple of g of x, a polynomial multiple of g of x. And so this should conjure up the following process. Run the division algorithm and show that the remainder is 0. That's what we're going to do. So we have, say, q of x and r of x in f bracket x, such that f of x is equal to g of x times q of x plus r of x, where the degree of r of x is strictly less than the degree of g of x. All right, so now our goal is to show that r of x is the zero polynomial. If we do that, then we show that f of x is a multiple of g of x, which means that it lives in this ideal, and that will give us the reverse containment. Okay, and let's think about this. We've done this kind of trick multiple times, right? When we run the division algorithm and then try to show that r is 0, what we often do is use some minimality condition, right, to actually force r of x to be the zero polynomial. So since f of x and g of x are in I, and in fact, let me be a little bit more precise. So here's what we know. F of x, of course, is in I. Also, g of x is in I. I is an ideal, which means that g of x times q of x is in I. So really, since f of x and g of x times q of x are both in I, we see, okay, so I is closed under subtraction, so we see that r of x, which is going to be f of x minus g of x times q of x, is an element of I. Okay, so now r of x lives inside I. The degree of r is strictly less than the degree of g. G is the non-zero polynomial of least degree, which means that every polynomial that has every polynomial in I that has degree less than g has to be the zero polynomial, right? So by minimality of the degree of g of x, we see, or we conclude, that r of x is equal to the zero polynomial. Therefore, we have f of x, that's going to be equal to g of x times q of x. Well, this is an element of, right? This is the form of the polynomials inside the ideal generated by g of x. And so, what do we have? The ideal, I want the other way around. So I is contained in the ideal generated by g of x. Now we have equality. So let's finish it off like this. Thus, I equals the ideal generated by g of x is principal. So what we did then is we showed that every ideal in f bracket x is principal, which means that f bracket x is a principal ideal domain. Now, this proof, if you note, this proof was constructive in the sense that it tells us exactly how to find a generator. It tells exactly who a generator for the ideal, any ideal in f bracket x is. So let's take note of this because we're going to need this fact. So note, the proof shows that any non-zero polynomial of least degree. Remember, the zero polynomial has degree minus infinity, right? And so the degree of every non-zero polynomial is going to be greater than or equal to 0. So you run through all polynomials in your ideal and just choose any one of them of least degree. So this shows of least degree generates capital I. Okay, so this next theorem, right, this one, so this is what, 27.11. I think this is one of the amazing results of ring theory. And so it goes like this. So let's let F be a field. And I need a polynomial and let's say a little f of x in f bracket x. So we're taking a polynomial whose coefficients lie in this field f. And then it goes like this. If, nope, not if. It goes then, the ideal generated by f of x is maximal if and only if the polynomial f of x is irreducible over f. So I don't know. I mean, it's sort of unexpected, I guess, or at least to me it is. When you first see this, I was really. I mean, once we see the proof, we'll see why it's true. But I don't know. I really like this result, and notice what it does. It gives a connection between polynomials, irreducible polynomials, and the quotients of f bracket x by ideals that form fields, right? Remember, maximal, you get a maximal ideal if and only if the corresponding quotient is a field. Okay, so let's see how this proof goes. So in the forward direction, we're going to assume that our ideal is maximal. So let's assume the ideal generated by f of x is maximal. Now, the first thing that we want to argue is that f of x it can't be a constant polynomial, so it's got to have degree 1 or greater. So first, note, and I'll say some words about this. So first note that f of x is non-constant. And here's the reason. So if f of x is the 0 polynomial, then the ideal generated by f of x is the 0 ideal, and that's certainly not maximal. So now, if f of x was a non-zero constant, so if f of x equals c not equal to 0, then remember, anytime if your ideal contains a unit, then that ideal is the entire ring, right? So then, then we'll say since C is a unit, right? The units of f bracket x are the non-zero elements of f. So since C is a unit, the ideal generated by f of x equals all of f bracket x, and so f bracket x is not maximal as well. All right, the entire ring is never a maximal ideal. You can say, and so f bracket x is not maximal. Okay, so what we've shown now, we are guaranteed that our polynomial is non-constant. So what's my goal? My goal is to show that f of x is irreducible. So let's say, suppose that f of x factors as g. I think I want to use g of x and h of x. Yep. So suppose f of x equals g of x times h of x, where g of x and h of x in f bracket x have degree less than the degree of f of x. In other words, we're saying suppose f of x is reducible. Now, let's see. Since well, let's see. Let's look at, so g of x times h of x, that's equal to f of x, which of course lives in this ideal. And let's see now, we're assuming that the ideal is maximal. Oh, wait a minute now. So let's see now, what did we prove? We proved that maximal ideals are prime. And so, and f of x is maximal, hence prime. Well, let's see, if we've got a prime ideal and a product lives inside the ideal, then one of the two factors has to be in there. So we conclude that g of x is an element of the ideal generated by f of x, or h of x is in there. So, or h of x is an element of the ideal generated by f of x. So if let's look at the first case. So if g of x is in the ideal generated by f of x, then, okay, so what does that mean? Well, it means that g of x can be written as f of x times some other polynomial. I'm going to call it r of x. So then g of x is equal to f of x times r of x for some r of x in f bracket x. Okay, so what does that tell us now? Notice what happens when you multiply polynomials. The degree cannot go down. It can go up, but it can't go down. So what does that tell us then? It tells us that the degree of g of x is greater than or equal to the degree of f of x. So it follows that the degree of g of x is greater than or equal to the degree of f of x. That's a contradiction. And then we would get a similar contradiction if h of x is in there. So a similar contradiction arises if h of x is in the ideal generated by f of x. All right, so we get a contradiction no matter what. And so what's our conclusion then? We never could have had a factorization like this in the first place. All right, so therefore, f of x is irreducible over f. All right, so what we know so far then, if we have a maximal ideal, right? If the ideal generated by f of x is maximal, then the polynomial f of x has to be irreducible. And now we're going to do the reverse direction. Okay, so, and we're just going to do this directly in the following sense. So let's assume that f of x is irreducible, and let's say j be an ideal of f bracket x such that the ideal generated by f of x is properly contained in J, which is contained in F bracket X. Okay, so what's our goal? If we want to conclude that this ideal is maximal, then what we need to do is show that J is equal to F bracket X. All right, so that's our goal now, is to show that J equals all of F bracket X. Now, what do we know about J? Well, J is an ideal living in F bracket X. What did our previous theorem tell us? It told us that every ideal is principal, which means that there is some polynomial that generates this ideal. So that's by our previous theorem, so 27.10. So by 27.10, J is equal to the ideal generated by some g of x, so equal to ideal generated by g of x for some g of x in F bracket x. Now, what do we know? Well, okay, so this tells us that f of x, this polynomial, lives in this ideal. So since f of x is an element of the ideal generated by g of x, we have f of x equal to g of x times, what do I call it here, h of x. All right, for some h of x in F bracket x. That's just what it means to live in the ideal generated by g of x, right? You could be written as g of x times some other polynomial. But wait a minute. F of x is irreducible. And now we have it written as a factor, or now we have it factored like this. Okay, so what does that tell us then? It tells us that one of those two polynomials has to be a unit, which means it has to be a constant polynomial. All right, so since f of x is irreducible, one of those polynomials has to be constant. So either g of x is constant, or h of x is constant. Now, constant polynomials, of course, those are units. And so if g of x is constant, remember what we know. Anytime if an ideal contains a unit, then it has to equal the entire ring. And so if g of x is constant, then J contains a unit. And so J equals F bracket X by, I want to say, is that 27.1? I don't remember. I didn't write down the theorem name. Or sorry, theorem number. It's whatever that, it's like, oh, let me look it up real quick. It's like 27.1 or 2. Ah, 27.1. Yeah, so this is so this would be by 27.1. If h is constant, wait, what? Oh, okay. Sorry, there's a little typo. Let me just fix that typo because that's bizarre. Sorry, 1 second here. Okay. So if So now let's consider the other case. So if h of x is constant, then let's give it a name here. So then let's write h of x equal to alpha, right, which is some non-zero element of f star, right? It's a constant polynomial. Just call that constant alpha. So now, what does that tell us? It tells us that f of x is equal to, so let's see, it's going to be g of x times alpha and so and so g of x, and I'm just going to solve for g of x equals alpha inverse times f of x. But this lives inside the ideal generated by f of x. And so what does that tell us? That tells us that g of x, well, if g of x lives inside here, then the ideal generated by g of x has to live inside here also. So this implies that the ideal generated by g of x is contained in the ideal generated by f of x, but we said that that's not the case, right? We have proper containment here. So a contradiction. This, I don't know, I just think this is a great proof and it's a great result. So I'm going to stop here and we're going to see applications of this theorem. I'll pick up with applications next time, right? But this is just a fun proof, right? In fact, both of these proofs, this is a fun day, right? 2 fun proofs. All right, we'll see you.